Hello, hi everyone. So welcome back to my channel and let's just quickly start with the today's question, minimum total distance traveled. So till now we have covered 20 challenges. In case you have missed any, you can watch it on my YouTube channel. I've created playlists for the same. So let's just read the problem statement. There are some robots and factories on the x-axis. You're given an integer array robot where robot of I is the position of the ith robot. You're also given a 2D integer array factory where factory of j is equal to position with a limit, indicates that position j is the position of the jth factory and that the jth factory can repair at most limit j robots. Okay, so the positions of each robot are unique. The positions of each factory are also unique. Note that the robot can be in the same position as a factory initially, and all the robots are initially broken. They keep moving in one direction. The direction could be negative or positive. When a robot reaches a factory that did not reach its limit, the factory repairs the robot and stop moving. At any moment, you can set the initial direction of moving of some. So in total, we have to return the minimum total distance traveled by all the robots. The test cases are generated such that the robots can be repaired. Right now, some things we have to note: all robots move at the same speed, so we don't have to have a check for the speed. If two robots move in the same direction, they will never collide. Okay, so they cannot move in the opposite direction crossing each other, they will collide. If two robots move in opposite direction, they meet at some point, they do not collide, they cross each other. If a robot passes by a factory that reaches its limit, it crosses it as if it does not exist. Okay, if the robot move from position x to y, the distance is absolute of y minus x. Okay, so we are good on the problem statement. In total, we have to return the minimum total distance traveled by all the robots such that they get repaired. Like, we will go with the examples while doing the intuition building part. So let's just quickly move to there. Okay, so we can quickly start with the intuition building part. So if you see that we are given these two basically arrays and we have provided with the robot, these are the position of the robot, and in the factory for each of this is the position of the factory and this is the number, the limit of the factory, right? So if you try making it on a number line on a x-axis, let's just say this is 0 1 2, we have maximum 6 positions for the robot and the factory, so 3 4 5 and 6, right? And if you see, we have a robot at 0th position, r is here. Let's just say we will name it r1, and r2 is at 4 and r3 at 6. So we have 3 robots and the factory is at this 2. So factory 1 is here and factory 2 is 6th position, and the limit of this factory is 2 and this is also 2. So at most it can repair 2 robots at a time. So this robot 1 can come to which factory? Nearest factory. This similarly for this robot, so the current frequency it has become for 2 to 1. Now it can come here. Yes, it can come here or it can come there also. R3, it will come where? It can come to this R2. It can come to F2 and it can also come to F1. But what we have to do, we have to calculate the minimum distance, right? Minimum total distance traveled. So we have to minimize the distance. If you see, we have to minimize this distance, total distance. How we can minimize? If we have, let's just say, first position of R1 as 0, so we need to somewhere pick the minimum position of F1 so that we can assign it to him, and after that the robots that come, they will be assigned to some later factories or this one only if the frequency, if the limit is there or not. So how we will divide it? Let's just say how we can do it. Write it 2 times. Okay, F1 is here and one more F1 is here. Similarly F2 is here and F2 is here. So when R1 come to F1, this F1 is already used. Now this R2 can come to this F1, then this F1 will be used and we are left with R3 and F2 with two limits. Or if F2 comes to this F2, sorry, if R2 comes to this F2, then we are left with one frequency of one limit of F2 and R3 can come to this. So this will minimize, because if this comes to here, the minimum distance it will travel is 2. 0 to 2 is 2 minus 0, 2. When this R2 comes to this 2, right? 4 minus 2 will be again 2, right? And this R3 will come to F2. So this will travel 0 distance. So 2 plus 2 is 4 now. Now let's test for another use case. R1 come to F1. Okay, R1 comes to F1. R2 will come to R this F2. R2 will go to F2 and R3 will go to F. Okay, so as per this, the total distance will be like R1 will be assigned to F1. So R1 to F1 will be again 2 size. R2 to F2, R2 to F2 will be again 2 size. So 2 plus 2, and R3 to F2, this is 6. So it will be 0. So answer is 4. Again we are getting 4, so the minimum distance will be 4, right? So now if you are seeing what is the approach that we are going, so now we are like finding all possible options, that if this R1 can go to F1 if there is a limit, similarly it can go to F2 also, but that will not give your best answer, right? So this R1 if travel to this F2, let's just say if R1 travels to F2, right, and this R2 travels to F1 and R3 travels to again F2, right? So this is 0 and this is 6 and this is 2. So this is giving you 8, but this is not your minimum distance, right? So you will not pick this. So we are seeing that we are trying every possibility, right? So this is, let's just say this is your R1, R2, R3, and this is your F1, F2. And as I have said that the frequency, that limit is this 2. This 2 is the limit. So what we can do, we can take it like this, 2F1, 2F2, right? So now we can try possibilities. This possibility R1F1, R2F1, R3F2, right? So one possibility is R1F1, R2F1, R3F2, right? And the next possibility, if we see, R1 will be assigned, let's just say again F1, we will fix this first. So R1 with the F1 only, but now we will change R2. So R2 will be now F2 and R3 will be again F2. Okay. Now we have fixed R1 F1 and we will interchange this R2 F1, R3 F2. So first we have assigned R2 to F2 and this is fixed. Now we can do same thing. R1 F1 will be fixed, R2 and F2 will go. So now we will assign R3 with F1, right? And these all can give you different answer, and out of these you will try to get minimum. Now you have fixed this R1 to F1. Now what you can do, you can fix this R1 to F2, right? This F2. So you can try fixing this. Now you try making your answer with picking, because one limit is left for this and two limit is left for this. So what you can do, either both of them will be F1. So R2 with F1 and R3 with F1, right? Now one of this and one of this can be picked. So R2 with the F1 and R3 with F2, or vice versa, R2 with F2 and R3 with F1, right? Now you are seeing that we are trying multiple options, R1 with F2, right? So these 6 options that we have checked, right, based on the limit and based on the number of robots we have, and out of these we will try getting our answer. So how you can do this in code? So we will try using recursion, right? So with recursion we know that there is a dynamic programming approach of 0-1 knapsack, right? Most of you heard of this. So in that approach, what we generally do, we take one or don't take one. So what we are doing here, either we will assign R1 to F1 or we will not assign R1 to F1 and we'll try assigning it to upcoming next factory, right? So if R1 is not assigned to F1, that means R1 is not being repaired now. So what we'll do, we will try assigning R2 and R3 for the first factory, then we try with R1 if there is any factory available, and that's how we will try getting our answer. And at some point we will get, so at some point we will get some options where some of the robots, because we are trying possibilities, right? Possibilities, because so there will be some possibilities where some of the robots are left to be repaired, and that will not give our answer, because let's just say like R2 is there, R3 is there, and F1 and F2 are there. So what you will do, you try assigning R2 to F1, or you will not assign this to F1. So one possibility is R2 F1, and one possibility you don't do anything. And one other possibility is R2 with F2, or if you not assign it to F2 again. So R2 will be left unrepaired in the third, here unrepaired R2. Similarly here unrepaired R2. So when any of the robot, when any robot is left unrepaired, it can be because the factory we are going, we will not add that robot in that factory for repairing. So if any robot is left unrepaired, that will not give us answer, right? So what we are doing here, either assign it to F1 or not assign to F1, right? If we are not assigning, then we will, what we'll do, we will try assigning the next robot to the F1 and try getting our answer. But that approach won't give our, but since we are doing every possibility, so we have to try this. So this is a recursion approach for this question, and we will try doing that. And so the time complexity, now the part comes for time complexity, right? So the recursion time complexity will be big of, as we see that we are trying every possibility, and the number of robots, let's just say RM, and the number of factories will be n. So the time complexity will be 2 to the power of m plus n, because we are trying every possibility. So this is a time complexity that we generally get in recursion, in the brute recursion, right, without any extra thing. And the space complexity will not be any, like if we are not calculating the recursion space, then it will be big of 1 only, right? Or we can say, okay, so now the space complexity for the recursion part will be big of m plus n, as it will take the recursive space. Now since this is a recursion, and in most of the approaches, like since we have a constraints of 10 is to power like 9, so that way this will fail. So what we can do to improvise on this recursion, we can do memoization, right? So the first step, whenever your recursive solution fails, you try doing memoization. What it is, that you try saving your already calculated answer, right? You try saving your already calculated answer in some storage so that you can use it later, right? So this is a memoization thing. So what we can do, since we know that for every robot we are like trying multiple options, let's just say that so this robot can come to this factory, this factory index is 0, let's just say the factory number is 2, okay, this factory number is 6, right? So this robot is either going to this or either going to this, right? If 0 robot is going to 1, one robot can go to 1 and one go to 2, right? One can go to 2 and 1 can go to, okay, 1 can go to 1, 1 can go to 2, right? Now if 1 is going to 1, that means 2 will be going to 2, right? Similarly, if 1 goes to 2, then 2 can go to 1 and 2 can go to 2. Similarly, if 0 is going to 1, let's just say there is other option, 0 is going to 2. So that's how we can build our recursion tree. And at some point, if you find that few of the options you will be gathering, because if you assign this 0 to 2, right, now 1 will be assigned with 2, this 1, okay, and we have already calculated, we have already encountered this with here when 1 is going to 1, right? So at that moment 2 can go to 2 and we can directly get our answer. So that's how, because when you try building recursion tree for every recursive solution, you find some points which you have encountered previously, and that's how you come to know that you have to do now memoization thing, this thing, right? So when you do memoization, so we will do while doing the coding part, that will make us more understanding, because when first we try writing this recursive solution, and the memoization thing is very simple, very basic thing. Once you get the glimpse of this recursive approach, you will already getting this answer. Now the time complexity will become order of m cross n, okay, and the space complexity of this solution will be big of m cross n, because now we are using. And one important thing that we have to consider, because as we have discussed that this distance r1 with f1 we have to minimize, right? And this array that we have this given, we can get this unsorted. Let's just say it will be 4, 0 and 6, right? So 4 robot will you can get first, and now your this factories array can be like this. How you can, so how you can know that this and your first robot and your first factory will be like, if you assign it to this you will get the minimum. So you have to do some sorting thing. So we can write it here, important thing, sorting, right? Sorting will help us reducing the distance, as it will like sort all the positions of this robot and factories. And if you start from first, or you can start from end only, both of will them will work. But if you start from the first or end, you try getting your minimum answer, because you try assigning it to minimum position. Okay, so now we will move to the coding part to get the more understanding of this approach, and we will try that memoization thing there only. So now we'll move to the coding part. Okay, we can start with the coding part. So first we will try the sorting. Okay, first we'll sort robot. So robot dot begin and robot dot end, right? Now similar thing we have to do for factory. So factory dot begin and factory dot end. Now we have sorted both the arrays. Now we have to create one other vector so that it can store the these factories, okay, with their frequency. So vector int factories, and we will go for each factory. So auto factory on factories, right? And first we get the position of a factory, so it will be factory of 0, okay. And now the limit, so limit will be factor of 1, right? Now we will go for int 0 till this limit, and we will try pushing all of the position again in this factory. So push back position, right? So since the limit is 2, so 2 will be pushed 2 times. Now 6 is 2 limit, so 6 will be pushed 2 times. That means position 6 factory is available 2 times, right? And that's how we can get our answer. Now what we do, we just have to call our function. Let's just say solve, or make it more minimum distance, right? And it will get the number of robots, like this will be position of the robot. So initially it will be 0 and factory position will be 0. Now the robot array is this, so we'll just pass it directly. Factory array will be similar, and okay, so these all are required, right? We just return it. Since it is a long, we have to create the same. So return long, and the name is minimum distance. And here we will write our logic for the recursion. Now the int current robot. Okay, current robot, because first robot is 0. This is the position, so robot will be 0, right? Similarly, current. Okay, so we have discussed that this should be robot number, not the position, right? That's a mistake. So current factory. Now this is robot, so we'll just directly pass this robot array, and this will be a factories. Okay, so my mistake. So this will be factories because we have populated this. Similarly, we will do it here, vector of int ampersand factories. Now what we'll do, we will first assign current robot to current factory. First we try assigning it. So long assigning, or we just name it assigned. So that will be, if the current robot is assigned to current factory, that will get our minimum distance from this current robot to current factory. So that will be absolute of your this robot array and your current robot. So this will get our position of the current robot, right? And if we subtract the factories, okay, so factories of current factory, right? So factories of current factory will give the position of the current factory. This is the number, so this will give the position, and difference of them will give the distance. Now since current robot is assigned to current factory, now we will check for the left number of robots from the left number of factories. So that will be, again we will call this function minimum distance, right? Minimum distance. Now the number current robot work is done, so we will update the current robot. Let's just do it this. Okay, so now minimum distance of current robot plus 1. Factory is also done, so we will update the factory. Now robot will be same, this array, and factories will be again same. So this is when the current robot is assigned to the current factory. Let's just say it is not assigned. Okay, current robot is not assigned to current factory. That means it can be assigned later. So what we'll do, we'll just get not assigned. So that will be, we just call this function because there is no work we have to do for the distance. So we'll just call our function again, and the current robot work is not done, so we'll just simply pass this. But we are skipping the current factory and we try getting our answer from the next factory. So we update the factory, current factory, and robot and factories array will be same. Okay, now we have both assigned and not assigned. And now how we'll get our answer? So we have to return the minimum distance. So minimum of assigned and not assigned, right? So this will get our minimum. Now when the robot, if we see, when this robot or the robot number 046, when we reach this robot, third robot, and the work of this robot is done, now what we have to do, we will update the robot, and there is no fourth robot. So what we'll do, we will check if current robot is equals to, the size of this is 3 and the indexing is 0 base. So if we reach here, so the index will be 3 and the size is 3. So we can directly compare if current robot is equals to robot dot size. That means all the robots work is done, so we'll just return 0, because this is the minimum distance that they can have. We don't have to do any work. So we can write it like this: if all robots are assigned to some factories. Now one more check. Let's just say we have skipped all the factories for this first robot or second or any, and all the factories have been done. So we can get some point that some robots are left. If all robots are done, then we can get direct answer from here, 0. But if some robots are left and factories are done, so what we can check: if all factories are assigned or not. Okay, if all factories are assigned or not can be possible, but we have reached the end. Okay, now we can directly check if your current factory is equals to your last factory next. So that will be this factory size, because all factories this done. So this, whether number of robots are assigned or not, that is not the case here. So if current factory is equals to factories dot size, that means there are some robots that are left. If all the robots work is done, the check will come here. If it is skipping this, that means some robots are left. Okay, some robots are left, and if some robots are left, we cannot get our answer directly, so we'll just return maximum, because what we have to do, we will try getting our minimum, so the maximum value that it can have. Okay, so it is a long, and so it can have maximum value of 10 is to power 12, so we can directly write 1e12. Okay, this is the expression for writing 10 is to power 12. So this is how we can do. Now we try running this. Okay, so where we are getting this error factor. Okay, so this should not be a factories, should be factory. So yes, it is running fine for this example test case. Let's just try to submit it, and we surely will get the time limit exceeded, because it will try checking for all possibilities. Right, we have got this. So what we can do here, we try memoization, because we are encountering some of the positions multiple times. So what we can do, we can create one memory. So vector of long, and it will be, let's just say dp. Okay, and it will be of size robot dot size of long. Okay, it will be of now factory dot size, sorry, factories dot size, right? Because this is the new factories that can have the maximum answer, maximum number of factories it can store. So factories dot size, and currently all are assigned to -1, because none of them are encountered before. Now we will pass this dp here. Similar thing we will do, copy this and add this here, right? And add a ampersand sign. Now this dp is passed into all the recursive calls. And how we can check before going to this minimum distance, we can directly check if dp of current robot and your current factory, right? If we have encountered this position before, that means we know that if we try assigning the robots, the left robots, from now on we will get some answer that we have encountered before. So if it is not -1, that is it means it can encountered before. So we'll just try to return this dp of current robot and current factory. And let's just say it is not encountered before, and first time we are encountering the current robot and with the current factory. So how we can populate here? So we will populate the dp of current robot, current factory with this minimum value of this. So this will populate, and whenever the same will be captured again, it will return from here only, right? So now we have to one checks that we have to pass the DPRA here and DPRA here, right? So let's just try to run it again. Okay, it is running fine. Now we try to submit it. Right, so we have submitted this successfully. Thanks everyone for watching. In case you do like this video, please do hit that subscribe button and turn on the notification so that we can solve these challenges together. In case you have any questions or comments or any suggestion, please do share that in the comments. I will review them and I will work upon them. And thanks for supporting me till now. And we have completed this all the challenges of October, and we will do it again in the November. Thanks everyone.